Earth has a radius of roughly 6,378 kilometers. But physically, human beings have barely scratched the surface. We cannot drill our way to the center. As we dig into the crust, the ambient temperature and crushing pressure rise rapidly, physically destroying our equipment. Our absolute physical limit is the Kola Super Deep Borehole in the Arctic. After 2 decades of drilling, scientists hit a maximum depth of 12 kilometers. Even our deepest active excavation sites, like the commercial gold mines in South Africa, which act as direct or pratyekshroot sources of geological data, bottom out between 3 and 4 kilometers. To put that in perspective, if the Earth were an apple, our deepest drills haven't even pierced the skin. We have to look for answers without digging. We do get some direct samples from deep below. Volcanic eruptions push liquid magma and solid rock to the surface, but a surface lava flow cannot tell us the specific dimensions of the mantle. To map the interior, we rely on indirect sources, or apratyekshroot. We measure anomalies in the gravitational pull at different latitudes. We conduct magnetic surveys, and we analyze the composition of meteors. But the most precise tool we have comes from earthquakes, specifically the seismic waves, Pukampia Terengane, that radiate outward when tectonic plates slip. By tracking how these vibrations move through the planet, seismologists can effectively perform an MRI scan of the Earth's interior. Every single earthquake starts at a specific rupture point deep underground, known as the focus, or Udgam-kendra. The location on the surface directly 90 degrees above it is the epicenter, or Adikendra. The energy released travels in 2 forms. Surface waves cause the visible destruction we associate with earthquakes, but body waves travel inward, directly through the planet. There are 2 types of body waves. Primary waves, or P waves, are the fastest. Like sound waves, P waves can pass through solid rock, liquid magma, and atmospheric gases. Secondary waves, or S waves, arrive later. S waves have a very specific physical limitation. They can only travel through solid materials. If they hit a liquid, they stop completely. As both types of waves travel deeper, the increasing density of the Earth's layers causes them to refract, or bend, changing their velocity and direction. That single mechanical limitation of S waves, that they require a solid medium, is exactly how we mapped the layers we can never see. When an earthquake hits, seismographs all over the world record the vibrations, but there are large regions on the opposite side of the planet where waves simply do not arrive. These are called shadow zones, or Chaya Kshetra. For P waves, there is a distinct dead zone. Between 105 degrees and 145 degrees away from the epicenter, seismographs record nothing. The waves are refracted sharply away by a dense boundary deep inside. The S-wave shadow zone is much larger. Because S-waves cannot travel through liquid, they hit the outer core and stop completely, creating a massive shadow covering over 40% of the Earth's surface beyond the 105-degree mark. This massive gap in the data is the definitive proof. The complete disappearance of S-waves past 105 degrees mathematically guarantees the existence of a massive liquid layer deep inside the planet. The absence of the wave is the evidence of the core. Let's map the structure from the top down. The outermost solid layer is the crust, or Bhupar Padi. Underneath the oceans, it averages just 5 kilometers thick. Beneath the continents, it expands to 30 kilometers. Underneath massive mountain ranges, the crust is even thicker. Beneath the Himalayas, it reaches a depth of 70 kilometers. We classify these crustal zones by their dominant chemicals. The upper continental crust is mostly silica and aluminum, known as Sial. The oceanic crust and upper mantle are silica and magnesium, called Sima. The distinct boundary where the crust ends and the denser mantle begins is called the Moho discontinuity. Directly below the Moho sits the asthenosphere, or Durbaltamamundal. Extending down about 400 kilometers, this layer is semi-solid and plastic. This is the primary source of the magma that feeds volcanoes. If we group the entire crust and the very top layer of the solid mantle together, we get the lithosphere, or Stålmundal, which ranges from 10 to 200 kilometers thick. Because the solid lithosphere rests on top of the plastic asthenosphere, it can fracture and shift, creating the tectonic plate movements that trigger earthquakes. Past the asthenosphere, the solid lower mantle extends downward to a depth of 2,900 kilometers. At 2,900 kilometers, the solid rock of the mantle ends abruptly. This boundary is the Gutenberg discontinuity, separating the mantle from the core. The core itself is split into two distinct layers: the liquid outer core, which creates the S-wave shadow zone, and the solid inner core. The transition between these two is marked by the Lyman discontinuity. Unlike the rocky crust, the core is intensely heavy, composed primarily of nickel and iron, a mixture known as knife. Temperatures in the inner core rival the surface of the sun, but the physical weight of the entire planet pressing down creates such immense pressure that the iron cannot melt. It is forced to remain a solid sphere. Let's review the mechanics that prove this structure. P waves pass through all states. S waves only pass through solids. This creates specific shadow zones, a narrow band for P waves between 105 and 145 degrees, and a massive blind spot for S waves everywhere beyond 105 degrees. Chemically, the layers progress from Sial in the continents to Sima in the oceans and mantle, down to the dense knife of the core. This table summarizes the physical boundaries. The Moho discontinuity separates the crust and mantle. The Gutenberg discontinuity separates the mantle and outer core, and the Lyman discontinuity divides the liquid outer core from the solid inner core. You don't need to guess what is beneath our feet. The Earth's vibrations map the interior for us.